Welcome back to our SQL learning journey. For our final week of the SQL learning path, we're going to dive into some of the more advanced and miscellaneous topics, the kind of concepts that really separate a casual user from a proficient database professional. These are the tools that give you immense power and flexibility in managing and querying data. Let's begin with a look at how we manage our database structure and ensure data integrity. First up, we have views. Now, think of a view not as a real table, but as a stored query, a virtual table. It's a way to simplify complex queries and can also be a powerful security tool. The syntax for creating a view is quite straightforward. You use the create view statement, followed by the name you want to give your new view. Then, you use the as keyword, followed by the select statement that defines what data the view will contain. For example, let's say we have an employees table with a lot of columns, and we frequently need to see a list of high-earning employees. Instead of writing a long select query every time, we can create a view. We would write create view high earners as and then our query, select employee ID, first name, department, salary from employees where salary is greater than or equal to 70,000. Now, anytime we want to see this list, we can simply query the view, just as if it were a regular table. Next, let's talk about constraints. These are fundamental to ensuring the accuracy and reliability of the data in your database. Constraints are simply rules that you enforce on the columns of a table. When we define these rules, we can ensure that, for instance, a column always has a value, that all values in a column are unique, or that a value falls within a specific range. The syntax for constraints is usually integrated into the create table statement. For example, to create a products table, we can define constraints for each column. We might set the product ID as a primary key, which means it must be unique and can never be a null value. For the product name, we can add a not null constraint, ensuring every product has a name. And for price, we can add a check constraint that specifies the price must be greater than 0. This ensures that no one can accidentally insert a product with a negative price or a missing name. Moving on to transactions. A transaction is a sequence of operations that are treated as a single, indivisible unit of work. The core idea here is the all-or-nothing principle. Either all the operations in a transaction succeed and are committed to the database, or if any one of them fails, they are all rolled back, leaving the database in its original state. The syntax for a transaction is typically wrapped in two commands: begin transaction and either commit or roll back. You start the transaction with begin transaction, perform all your SQL statements, your updates, your inserts, and then, if everything looks good, you issue a commit command to save the changes permanently. If something goes wrong, you use rollback to undo everything and return to the state before the transaction began. A classic example is transferring money between bank accounts. You have two steps, a debit from one account and a credit to another. You wouldn't want the debit to succeed if the credit fails. So, you put both operations in a single transaction. You begin transaction, then update the first account's balance to deduct the money, then update the second account's balance to add the money. If both updates are successful, you commit. But if there's an issue with the second update, you roll back, and the first update is undone as well, ensuring your data remains consistent. Now, let's shift our focus to some of the built-in functions that help us transform and manipulate data. These are incredibly useful for getting exactly the data you need, in the format you want. First, the mathematical functions. These are used for performing calculations. Common functions include round, which rounds a number to a specified number of decimal places, and floor, which rounds a number down to the nearest integer. As an example, if we want to calculate a price with tax and round it to 2 decimal places, we can use the round function. We would write a select statement to get the product name and price, and then for our third column, we'd say round, price multiplied by 1.12, as price with tax. The result would show us the product's price, and the new calculated price, rounded to 2 decimal places. String functions are used to manipulate text data. Functions like CONCAT for joining strings or upper for converting text to uppercase are common across many systems. For an example, let's say we want to create a formatted name from the first and last name columns. We can use a combination of string functions. We might use upper, substring, first name, 1, 1, to get the first letter of the first name and make it uppercase, then concat that with a period and the last name. The result would be something like JDO. Next are date functions, which are crucial for handling and extracting information from date and time values. These functions can vary a bit between different database systems. A common example is calculating the number of years an employee has worked at the company. We can use a DATEDIFF function, passing in the current date and the employee's hire date. We'd then divide that result by 365 to get the approximate number of years of service. Conditional expressions are powerful tools for applying logical rules within a query. The most common of these is the case statement. The syntax is almost like a programmatic if-then-else block. You start with case, then you have one or more when clauses, each with a condition, followed by a then clause with the result to return if the condition is met. You can finish with an optional else clause for any values that don't match your conditions. For example, we could categorize employee salaries. In our select statement, we would have a case expression. When salary is greater than or equal to 75,000, then high earner. Then, when salary is greater than or equal to 60,000, then mid-range earner. And finally, an else entry-level earner. This allows us to create a new, descriptive column that categorizes each employee's salary. Another crucial conditional expression is COALESCE. COALESCE is a function that returns the first non-null expression in a list. A perfect example is handling an employee's contact information. What if an employee's email is null? We can use COALESCE to provide a fallback value. Our select statement could be select first name, last name, COALESCE, email, no email provided, as contact info from employees. The query would then display the employee's email if it exists, and the phrase no email provided if it's null. Now for the final frontier of our learning path, advanced queries and window functions. These are used for powerful data analysis without collapsing your original rows. A top-n query is a technique for retrieving the top-n rows within a specific group, for example, the top 2 employees in each department. This is most effectively done using window functions. To achieve this, we can use a subquery. First, we write an inner select statement that uses row_number, over, partition by department order by salary desk, to assign a row number to each employee, ranked by salary, but restarting the count for each department. Then, we write an outer query that selects from this subquery and simply filters for all rows where the row number is less than or equal to 2. This gives us the top 2 highest paid employees in every department. Finally, let's distinguish between the powerful ranking window functions. They all assign a rank to rows within a partition, but they handle ties differently. The syntax for rank is rank over, partition by required constraints, order by required constraints. It assigns a rank to each row, and if there's a tie, the tied rows get the same rank, and the next rank number is skipped. So, you might see ranks of 1, 1, 3. For dense rank, the syntax is similar. The key difference is that it assigns a rank without skipping numbers for ties. So if 2 people are tied for first place, they both get rank 1, but the next rank will be 2, not 3. Understanding these subtle differences is key to performing accurate data analysis. You'll choose the right function based on whether you want to account for gaps in your ranking. And with that, we conclude our final lecture on SQL. I hope this interactive journey has given you a solid foundation for your future work. In the next video, we will have a look at some SQL interview questions. Thanks for watching this video. And if you watched this far, then please give it a like, share it with your friends, and do subscribe to the channel. See you in the next one. Till then, happy learning.